What I'd like to speak about with you is the application of some of these data analysis methods to problems from cosmology. So this fits into the data lifecycle concept that Rich was describing in the sense of we're going to look at massive archives of data and what can we learn and analyze and therefore improve our understanding of using those archives, in this case from the Dark Energy Survey. This is joint work with Eric Huff and Uma Rebapragada at JPL, and also Tim Eifler at the University of Arizona. And I'm in the machine learning group at JPL along with Uma. Eric and Tim are from cosmology. So starting out with some motivation about what we actually want to do from the science perspective, we are looking at, as I said, data from the Dark Energy Survey, which has the grand goal of improving our understanding of the universe's formation and evolution over all of time, basically. One way to do that is to construct a cosmological model of how the universe and its structure evolves. And this currently can be parameterized, depending which model you're using, by 6 to 10 parameters that dictate how things start, how they evolve, and what we see now. And a couple of those parameters are the amount of dark energy and the amount of dark matter in the universe. So you can see in this pie chart on the right, the matter that we can actually see with our eyes or other sensors, which is listed as atoms there, is less than 5% of what we believe the universe is actually composed of. So that's a very tiny fraction. The rest of it being composed, about a quarter of it being dark matter, and the bulk of it being dark energy. And all of them are dark in the sense that we cannot directly observe them, unfortunately. So we have to come up with ways to infer their presence because they have a large influence on what this model can tell us about how things are evolving. So at a very high level, the dark energy that's present is what's driving the acceleration of the expansion of the universe. And also at a very high level, the presence of dark matter is what drives the clustering of galaxies together because it exerts a gravitational force upon them. So those two factors have influence over time, and we want to figure out, where and how much of them are present. So one way to, as I said, infer their presence, for example, with dark matter, is to look at what are called weak lensing galaxy observations, which relies on the concept that if you have matter there, even if you can't see it, it is going to exert an effect on structures around it. So let's imagine maybe there's something in the middle here and you have a bunch of sources. If there's no gravitational effect, you might just expect them to be distributed as follows. Yet, if you have something in the middle that is actually massive, it will bend the light coming from sources that are distant and behind it and cause this lensing structure which distorts the shape of the galaxies, in this case, around that central point. So even though you can't see it, you can infer it's there by what it's doing to the light from the other objects. And then you can infer something about dark energy by looking at how that dark matter quantity changes over time and its distribution. And by time, of course, in astronomy, we can use distance as a proxy for time because the very, very remote sources are those from which their light is coming from many, long time into the past. So we can look at those distribution changes as a function of distance from where we're observing. But this is a greatly exaggerated effect in this diagram. This is not what the sky actually looks like. So it's actually much, much more subtle than that. And that means that you can't estimate those properties from only 5 or 10 or 100 or 1,000 observations of galaxies, but instead you need millions of them to do this well. And that's where the Dark Energy Survey comes in, which surveyed 5,000 square degrees of the sky, southern sky, over 6 years from using a telescope in Chile. And it looked at 400 million objects, which included both stars and galaxies, works out to about 310 million galaxies. And that's great. You have a very large sample, but if you have errors or systematic problems in those in that sample, then that's going to bias your estimate of what those dark energy and dark matter properties are. So it's extremely important that when you take that very large sample, you can do a high-quality filter to only retain the ones that are going to have the right information for estimating those properties. So our goal is to mine through that catalog, find the outliers that may be polluted by noise, artifacts, or other problems, so we can filter them out and keep the clean sample for estimating cosmological parameters. This gives us two benefits, basically. By finding artifacts or problems within the data, especially ones that aren't already known by the survey, which of course does its own quality filtering up front, that can actually inform improvements to the processing pipeline that's going back and processing these hundreds of millions of objects as we discover new and stranger effects that may reside within the data. And then secondly, of course, it has a science benefit here for the cosmological model. There's also the possibility that we will discover, buried within this very large archive, new objects that aren't previously understood or known. So there's a lot of benefits just from looking for weirdos within the data set. The data set we're working with is the object catalog created by the DES, which proceeds roughly in this order. We first observe, the survey itself has observed the sky at 4 different photometric bands, and you can see them listed here, G, R, I, and Z. We're not using the Y band. These are rather broad wavelength coverage that gives us a sense of the properties of the object across different wavelengths. And the goal is to observe the entire sky that we're looking at, the 5,000 square degrees, at least 10 times. So get at least 10 exposures of all of that, where each exposure is 90 seconds in duration. And that means, interestingly, and this actually matters for our analysis, that you might get the green band or the G band observed on one date, but the R band on a different date, and so on. These are not necessarily taken contemporaneously, but they're actually spread out over the 6 years of the survey. So, and you'll see why that matters in a bit. Next, you take the images of the sky, find the bright sources within it, which are going to become individual objects, and match that to reference catalogs so that you can have some confirmation that what you're seeing is or is not a known star, for example. Then each source is modeled using something called NG-mix, which is a 2-dimensional Gaussian mixture model applied to the 2-dimensional images to try to separate out sources, especially if they're nearby and their light is being combined. You want to be able to try to separate that out. Then you extract descriptive features, which are the flux at each of the bands of interest, G, R, I, and Z, but also shape features, estimates of the shear or the other distortions that are being, that the light from that object are being subjected to, other descriptive features like that. And then the survey itself, in the process of generating these objects, it provides several quality flags or features you can use to filter out things to try to get a clean sample. So we did that and found that discarded about 2/3 of the objects. So you can see that it's already a pretty strict quality filter. But I will say we still find that there are artifacts buried within what remains, which should be the good quality stuff, which underscores the need for this kind of work. So once we have that relatively clean sample that we're going to start analyzing, we use 2 different methods to look for outliers or artifacts within that remaining data set. And these are the 2 methods we're using: the isolation forest, which gives you a ranking of everything in the catalog by its isolation score, and I'll explain what that is in a minute. And also a method called Dmode, which seeks to find a diverse set of unusual objects within the sample, with the idea that once you've seen one example of a strange phenomenon, maybe you'd like to move on to something really different and quickly discover all of the different kinds of outliers present, rather than just getting a full ranked list of all of them. But both of them are valuable for this kind of investigation, which is why we're pursuing both of them. So a quick description of how the isolation forest works. Let's imagine we have a very simple 2-dimensional data set, because that's easier to visualize on the screen here. And what you do is construct a forest, so multiple instances of random decision trees. I'll explain why random in a minute. And then once you have this collection of, let's say, 100 random decision trees, you use them to compute an isolation score for every item, which is the average depth that that item appears in the tree. So here's how that works. Let's think about one random decision tree. What this does is randomly pick a feature, either in this case X or Y. So let's say it picked Y, and randomly pick a threshold value, which is A here. And everything that's above the line is going to go to the right, and everything below the line is going to go to the left. So that splits your data once. And then for each branch, you do this again. So over here, randomly pick a feature. This time it picked the X, and it picked a random B threshold. Everything to the left will go here. Everything to the right will go here. And then you recurse again, and everything over here from the C, everything to the left goes here, everything to the right goes to the right. But what's interesting here is there is, in fact, only one object left in this cell that has now been defined by these random splits. And therefore, you can't break that down any further, so it has now been isolated. So this object has a depth of 3 in this tree because it took 3 random splits to get it into its own box. You do this with the entire data set, and every point will get a score. And then you do this many, many times for each of your trees, and then this might end up with a score of 5 in a different tree, or 17. But on average, it will probably have a pretty low score because it's, on average, likely to be split with very few of these splits. But other items, such as this one, that's in the middle of that cloud, will on average likely take far more splits before it can ever be isolated because it's in a really dense region in the distribution. And here, in this case, it took 11 random splits, and each tree would give it a different number. So you can see how overall, hopefully, this is telling you which items are not representative of the whole data set. That's the brief intro to isolation forest. And then the brief intro to the Dmode algorithm, which, again, is going to look for diverse things, not necessarily a global ranking, is that it uses an incrementally growing model of what you have already seen and therefore presumably know about your data set. So if you have 300 million objects, there's no way to reasonably expect that you understand that full cloud or even can really look at it. But what you can do as a human is look at one at a time. And each one teaches you something new, ideally. So let's imagine that this algorithm is going to try to order those to teach you maximally new information about them. And the way it does that is by selecting the item that is most difficult to model using its model of what you already know about this data set. So very abstract, let's imagine we're looking at geometric shapes, and Dmode picks out a blue square as, hey, here's an interesting object. And therefore, you know about blue squares, and the model is blue squares. So it's pretty straightforward. The next thing it tries to pick something as different as possible from what you've seen before. So maybe it picks a red circle. So now you know about 2 possible objects in this data set, and the model is going to try to kind of bring them together. So it knows about square things and round things, and it knows about red and blue, so maybe some purple is kind of an average sense, and so on. If it picks something really different, it tries to grow the model, and each time it's projecting all the rest of the data points onto that model and saying, what fits the worst? What will teach us something new? And mathematically, what's going on is that everything in that learned set becomes D, your data set, and you're doing a singular value decomposition on that collection of objects, not on the full data set, which again might have like 100 million objects in it, just on this small set that the human has actually looked at. So this model, in particular the U, which are the principal component vectors of this decomposition, represents the knowledge that's in here in some usually a reduced form. So we select only, say, the top K principal components. Who's familiar with PCA, SVD type analysis? Yeah. So this should be pretty familiar. And this is how this algorithm tries to optimally select new items that you will learn something new about. So now you have some sense of the techniques that we're using. The more interesting thing from the science perspective is, okay, well, what have we found? I mentioned that there are 310 million galaxies in the data set. We selected a 10% spatially sampled subsample just to do our initial analysis, just to keep that more manageable. And then after applying the quality filters, again, that threw away 2/3. So we ended up with 12 million objects we're working with for this analysis, which is still a pretty large sample. And the representation we're using is the R-band luptitude. So ds measures the flux that gets converted to a magnitude, or optionally, what's called a luptitude. Who knows what a luptitude is, out of curiosity? Lots of you, awesome. It's just, you can think of it like magnitude, but it behaves better for very faint objects. So there's some good properties there. We look at that for the R-band, and then also color measurements of the differences we observe between I versus R, G versus R, and Z versus R. Each algorithm, we allowed to select the top 1,000 outliers from those 12 million. So 1,000 is kind of a lot for a human to look at, but as you can see, it's a very tiny sample of the entire data set. We developed a web-based outlier explorer that looks like this. and you don't need to be able to read all the content here. I annotated it. So it picks out, say, this object, which we're visualizing in RGB, and then you have the G, R, I, and Z individual observations. We have what the NGMix model predicted this should have looked like. Just the object in the center. It's ignoring nearby objects. I'll talk to you about the explanations that are automatically generated by the system to say why this object was picked. And then it also allows us to look at what are other surveys seeing at this sky position, in this case, WISE and GALEX. And then ultimately, we want to be able to classify, okay, is this outlier something that indicates a problem with the processing pipeline, some kind of problem with the detector? Is it something scientifically interesting? You know, what is this? So that's this final step of being able to actually classify what kind of outlier or anomaly this is, because that dictates how you're going to take that and inform an improvement to the survey or increase our understanding of the science going on. So here are some examples of what our algorithms have found within this data set. Again, there might be multiple objects within these cutouts, but the object that's supposed to be there should be in the very center. So here is an example where, to the eye at least, there's like nothing there. But the model actually generated something there, like a ghost object, or possibly one that's pulling in light from these nearby objects. Maybe they weren't correctly masked. So you definitely don't want this to feed into your cosmological model estimation because it's not a real object. These are the kind of things that we definitely want to pull out. And we have a couple of like this. In this case, it definitely looks like light is being blended between other sources and affecting the one that's supposed to be represented by this model. In other cases, we see, remember, each exposure is 90 seconds, so that's kind of a long time to be staring at the sky if you have anything nearby and bright that flies past. So these are almost certainly not red, green, or blue things, but of course, it just means that at that one band, at that one time, a satellite or aircraft just streaked past the detector, and it lit up in exactly one band, which is now being visualized as that band's color, right? So these, you would ideally hope, would already have been filtered out, but we find they are still present within the data set. So it's good that we can now hopefully clean them up. Here's another cool example where, again, the object should be in the middle, and it should definitely, if it's a real object, not be moving with respect to these co-registered images. So what you're seeing here is almost certainly, again, an effect of the fact that we're taking these observations of the bands at slightly different times. These could be separated by exactly 90 seconds, for example, if we do green or G and then R or something like that. So probably we think these could be something like an asteroid, not moving as fast as these guys, right? It doesn't streak across the entire field of view, but clearly it's moving between exposures. And it's not present in all of them, which is another big clue. So we also don't want these to factor into our estimates of dark matter or dark energy. And then we have found some interesting outliers from the science perspective. Who's familiar with green pea galaxies? This is a discovery that came out of the Sloan Digital Sky Survey data, actually by citizen scientists in 2007. And once some of these were found, of course, more were identified as being an interesting class of unusual galaxies. In this case, what we know at this point is that they have very low mass and they exhibit a high star formation rate. And we believe that these were probably more common in the early universe and less common now. So they're interesting for their own properties, but even to the eye, you can see that the color is interesting, which is, of course, what made them initially stand out. So those 4 bands we're observing at, these jump out as being interesting, but they're not problematic. They're actually interesting from the science perspective. Now, critically, it's not enough for an algorithm to tell you, hey, there's an outlier, but it should really be able to also tell you why it was picked, right? The isolation forest, as we discussed, can show you, hey, it got isolated because it had few splits to reach it. But we can also look at the actual data distribution plot. This is all 12 million objects represented, and this object, whatever it is, appears here if you plot 2 of those features, the R band leptitude and then the I minus R color, which means that this is very, very low on the leptitude scale, which means it's extremely, extremely bright or unexpectedly bright in terms of the full distribution for the R band. However, it's not anomalous. it's not anomalous in the y-axis, right, if you just project that. So it's the combination of them that's interesting. But looking at one two-dimensional plot is not fully depicting what's in the data set. So what we actually have, I have boxed in red the one we were just looking at, but if you zoom out, we have these for all pairs of features within the data set, as well as the one-dimensional distributions and where this outlier appears. So it's definitely an outlier in the R band, but it's really not in the other three. So this is the kind of thing you might not pick out as a global outlier. It's more subtle than that, but it's an outlier because of its location across all four. And specifically, the Dmode algorithm can tell us, hey, my model said these are the 4 values we should have seen for the 4 features that are being used, and look, it dropped way, way lower in R-band leptitude than I would have predicted, which means it was brighter in red than it should have been, given what else we've observed for this object. So that can give you some clues as to why this was selected and why it might be interesting. And you can actually look at the individual band images as well to further understand that. So to summarize, our goal was to find outliers within this very large catalog, both to improve the data processing pipeline by further filtering out things that we don't want to contribute to our science investigation, but also potentially to find new kinds of objects. This is it's in process right now, so we don't have it fully published, but our goal ultimately is to publish a catalog of the outliers themselves so other people can use them as an additional filter or as a source of objects to follow up, like with observations from Palomar or other telescopes. We use 2 different outlier detection methods that can give us different angles on what outliers reside within the data. And this exact same kind of technique can easily benefit other large surveys coming up. I've listed a few here. And we've also used this for other applications like Kepler light curves or looking at stars that are being observed by UCERT and other telescopes. So I'll just conclude by emphasizing my primary message here, which is that I think it's vital we have explanations for what comes out of these automated algorithms, especially when you're working with large data volumes. And I want to thank the JPL R&TD program for the funding support, and Brian Scott, a grad student at University of California, Riverside, for helping us with the initial analysis of this work.